Hello, I am Ori Plonsky from the Technion in Israel, and this talk is recorded for the conference on Bridging Disciplinary Divides for Behaviorally Modulated Mathematical Models in Human Epidemiology. I will talk about behavioral phenomena and their connection to epidemics. Over the past 70 years, and particularly over the last few decades, we see more and more evidence that people's behavior departs, sometimes sharply, from the predictions of the rational model. In this introduction talk, I will review some of the evidence for this, focusing on some of the most relevant behavioral phenomena to model behavior in epidemics and how we can integrate these into epidemiological models. Two major lines of research in behavioral economics are intuitively relevant for behavior in epidemics. The first involves people's decisions under risk and uncertainty, meaning mainly how people choose actions when the outcomes of these actions are uncertain at the time of decision. Specifically, because outcomes are probabilistic, this is clearly relevant for epidemics, since epidemics are by their nature uncertain and probabilistic. As I will show, under this umbrella term, decisions under risk and uncertainty, it will be useful to distinguish between decisions from description and decisions from experience. I will explain this distinction in a few slides. A second major line of relevant research in people's decisions is in strategic and social contexts, meaning that the outcomes of the choices that people make depend not only on the decisions that they make, but also on the decisions that other people make. Again, it is straightforward why this is relevant for epidemics in which people's decisions and their outcomes are clearly dependent also on other people. Again, it will be useful to distinguish here between other regarding preferences and social learning. Let me start with decisions under risk and uncertainty. In this domain, there is no doubt that the most celebrated and successful behavioral model is prospect theory, suggested by Kammer and Tversky in 1979. Prospect theory captures two behavioral phenomena that are intuitively relevant in epidemics, namely loss aversion and overweighting of rare events. Here's a demonstration of loss aversion. Imagine that you have the opportunity to play a gamble that offers a 50% chance to win $2,000 and a 50% chance to lose $500. Would you play the gamble? If you are like most people, you will reject this objectively attractive offer. The high rejection rates here can be explained with the assertion that losses loom larger than gains. That is, people dislike losses to a far greater degree than they enjoy equivalent size gains. Here's a demonstration of overweighting of rare events. Kammer and Tversky asked participants to choose between S1, which is winning 5 for sure, and R1, which is winning 5,000 with probability 0.001. Most participants here chose R1, suggesting most people prefer a lottery ticket that provides a small chance to win big over the expected value of this ticket. Kammer and Tversky also asked people to choose between S2, losing 5 for sure, and R2 that gives a loss of 5,000 with probability 0.001 and 0 otherwise. Here, most people chose S2. This suggests that most people preferred paying a small premium as insurance, 5 for sure, and this insurance protects them from a small chance to lose big. This illustrates how many people choose to buy both lotteries and insurance, a phenomenon that the rational model finds hard to explain. But it can be explained with the assertion that people overweight rare events, that they give a small chance to win big in the first problem and to lose big in the second problem more weight than it deserves. Overweighting rare events is a particularly interesting and relevant phenomenon for modeling behavior of people in epidemics. Simply, the outcomes of people's decisions during epidemics involve rare events. It is, of course, a rare event that the decision not to wash one's hands or not to put a face mask properly or to visit one's elderly relatives ends up in a catastrophic outcome. But if people indeed overweight rare events, then we may expect them to be even more careful and cautious than the true risk prescribes. Of course, this is probably not what we see in the current pandemic. it is hard to say that the average person indeed behaves even more cautiously than the true risk of the virus implies. One possible reason for this discrepancy is the fact that natural decisions of this type, visiting my parents or not, wearing the mask properly or not, these are made repeatedly and can be based on feedback from previous similar decisions. Prospect theory applies to decisions from description, decisions that are made based only on the description of the choice task. It turns out certain types of deviations from the rational model, especially those prospect theory predicts like loss aversion and overweighting rare events, are not robust when people make decisions from experience. These are decisions that people make when they can also rely on feedback from previous similar experiences. Let's see an example. Consider the following problem. Choose between S winning 60 for sure or R winning 40 with probability 0.6 and losing 15 with probability 0.4. The expected value of gamble R here is 18. So expected value maximization implies choice of R. Loss aversion, on the other hand, implies choice of S. So as to avoid a potential loss from R. We previously let participants make choices between S and R here, but we asked them to make these choices repeatedly 25 times. In the first 5 times, they did not get any feedback on their choice. Then, starting the 6th round, they got feedback on the outcomes of the possible alternatives. When making these 5 initial choices without feedback, people's decisions were indeed consistent with loss aversion. So the first block here shows how people were more likely to choose the safe option that avoids losses, although it has a lower expected value than the risky gamble. Yet, very soon after they started getting feedback on their choices, this bias was eliminated. On average, already in the first 5 trials in which they got feedback, the second block in this plot, they were actually slightly more likely to choose a risky option that involved losses. Recall, here these are the same people making decisions in the same task. The only difference is the availability of feedback. Loss aversion was eliminated. Even more interesting here is the observation that feedback not only eliminates, but actually reverses the way people behave in the presence of rare events. Look at the following example. Choose between S, losing 1 for sure, and R, losing 20 with probability 0.05 and getting 0 otherwise. This task is very similar to the example from earlier concerning the purchase of insurance. Here, again, we let people make 25 choices, the first 5 without feedback, and the rest with feedback. In the first 5 rounds, there was a slight bias towards the safer option as predicted by prospect theory. But once people started getting feedback, starting block 2 here, they were more likely to prefer the risky option of losing relatively a lot with a small probability over the expected value of this gamble. This suggests that people started behaving as if they underweight rather than overweight the rare event. This distinction between the way people tend to behave when they can only rely on a description of the incentive structure and the way they behave when they can also rely on their past experience through feedback of past choices, this is called the description experience gap. And this is particularly pronounced in settings that involve rare events. So when people got feedback, they started behaving not only as if they do not overweight rare events, but as if they underweight rare events. In other words, they started behaving as if they believed it won't happen to me. This tendency is highly robust and has been replicated in hundreds of experiments. Of course, this is very relevant in epidemics, in which thinking it won't happen to me will eventually lead to complacency and reckless behaviors that may hasten the spread of the epidemic. One way to capture this robust tendency is to assume that people rely on small samples of past experiences. The idea here is that when they face a decision, people first recall from memory a small number of experiences that they consider to be the most relevant to the current decision. And then they do whatever worked best, on average, in these relevant experiences. Why does reliance on small samples capture underweighting of rare events? Note that a mathematical property of small samples is that they tend to underrepresent rare events. So agents who rely on small samples will, more often than not, behave as if they underweight rare events. To illustrate this, consider again the previous choice task. Choose between safe, that gives a sure loss of 1, and a risky option that gives a 5% chance to lose 20. Say that these boxes here are the boxes of past experiences that the agent sees with each of these two options. Each ball here represents an experience that the agent received from choosing one of these options, and the numbers on the balls represent the outcomes that were received in these experiences. Say the agent takes a small sample, size 5, from each of these boxes. First, the box from the right, the safe option. Any sample taken from previous experiences of the safe option would look like this and result with an average outcome of -1. Yet most samples of size 5 taken from the left box that contain previous experiences with the risky option would look like this, simply because the -20 ball is unlikely to be picked when we draw only 5 balls from this box. The average outcome in this sample on the left is better than the average outcome of the sample from on the right, from the safe option. Therefore, reliance on small samples here prescribe behavior that looks like underweighting of rare events. The assumptions of reliance on small samples has several attractive properties. First, it can be the result of many different cognitive processes, so it is plausible in a way. For example, it can be the outcome of cognitive limitations like forgetting. Because people do not remember everything that happened, they will rely on only a small sample of past experiences. But interestingly, it can also be the result of cognitive sophistication. The idea here is that our minds are built to detect environmental patterns, and therefore they tend to discriminate between many past experiences, choosing only those few that appear most relevant to the current pattern that is detected. A second attractive property of reliance on small samples is that it is descriptive. It captures many different behavioral phenomena that emerge when people can rely on feedback on previous decisions. Here's a list of some of these. Third, and importantly, this assumption is predictive. That is, it is a highly useful assumption to make in models that are designed to predict choice behavior when people can rely on feedback. This was shown in a series of choice prediction competitions. In these competitions, organizers first collect training data that will be used for model development. The data is made publicly available, and other people are challenged to submit models that will compete in prediction of similar but different data. Only then is the test data collected, and the submitted models are evaluated based on their ability to predict behavior in this test data, pure out-of-sample prediction. It turns out that in these competitions, the best performing models consistently used the assumption that people rely on small samples. Now, as I said, because of underweighting of rare events, reliance on small samples predicts that in epidemics, people will behave recklessly. Let's demonstrate this again with the following reckless or responsible task. Here, reckless gives -100 if event E occurs and +10 otherwise, and responsible gives -40 if event E occurs and +5 otherwise. The chance that event E occurs is 10%, so most of the time, reckless provides a better outcome than responsible. Event E here may abstract the event of catching the virus, perhaps even carrying it unknowingly. Hence, it is relatively rare, and leads to losses regardless of one's choice. But if E happens, then the reckless behavior that could be abstract, for example, visiting one's parents without social distancing, gives an outcome that is much worse than the outcome of behaving responsibly. We simulated the behavior of artificial agents who rely on small samples in this task. And as can be seen, they indeed learn quickly to choose reckless behavior, although its expected value is lower than that of responsible. But reliance on small samples has another attractive property. Early in the pandemic, we saw a lot of this: empty shelves in the toilet paper aisle. This initially appears inconsistent with underweighting rare events, since this is clearly an overreaction to the possible risks rather than an underreaction. So what's going on? As it turns out, this phenomenon, the empty shelves on toilet papers, can also be predicted by reliance on small samples. Specifically, reliance on small samples predicts that most of the time, people will behave as if they believe it won't happen to me, and that in a significant minority of the time, they will have the exact opposite bias. That is, they will behave as if they overweight rare events. We demonstrated this using this panic or responsible task. Here, we just took the previous task, the reckless or responsible one, and replaced the reckless option from before with a panic option that provides the expected value of that option with certainty. Here it's -1. Choice of panic here can abstract, for example, hoarding of toilet paper, with event B being a shortage of supplies. So most of the time, and on average, being responsible and not needlessly hoarding supplies is better. But in the rare occasion of a shortage, those who panicked have it better off. Again, we simulated reliance on small samples agents in this task. As you can see, here around 40% of the time, reliance on small samples implies overweighting of the rare event and choice of panic. That is, reliance on small samples actually predicts a bimodal reaction to rare events, most often underweighting, but in non-negligible portion of the time, overweighting. To see why this happens, consider again this illustration from before. As I mentioned, most of the samples from the risky box will not include the rare event at all. They will look like this. But in those samples that will happen to include the rare event, the rare event will actually have a larger weight than it truly deserves. Objectively here, the rare event only happens in 5% of the times. But in this sample, if it appears there, it will get a weight of 20%, assuming, of course, that all balls in the sample are equally weighted. Next, let me turn to strategic and social decisions. The basic way to study such decisions is by studying economic games. Probably the most famous and familiar economic game is the prisoner's dilemma. In this two-person game, here on the right, each player chooses to either cooperate, marked with C, or defect, marked with D. The outcome that each player gets appears inside the cells of the table. For example, if both players cooperate, they both get, in this case, +1. If they both defect, they both get, again, in this case, -1. What makes this game interesting is that when one player cooperates and the other defects, the defector gets a high outcome, here it's +10, whereas the cooperator gets a low outcome, here -10. This then means that regardless of the action of the other player, choosing defection always yields the better outcome and better than choosing cooperation. That is, defection is a dominant strategy, and it is of course the prescription of the rational model for the one-shot game. However, experiments show that many people cooperate in this game. This is a clear violation of the rational model. One possible way to explain this is the idea of other regarding preferences. While the rational model assumes people are completely self-interested, other regarding preferences is the assumption that people also care about what other people get. This can explain cooperation here, because if a player dislikes or suffers some disutility from another person's loss, then cooperation may be worthwhile. This can, of course, be relevant for epidemics, because if people care about what others are getting, then they may be more inclined to behave responsibly, so they could avoid hurting other people. Now, this is the one-shot prisoner's dilemma game, but as I repeatedly mentioned, I think decisions relevant in epidemics are much more likely to be those that are made repeatedly over time with feedback. Interestingly, Playing the prisoner's dilemma game repeatedly with the same person actually tends to increase cooperation rates. For example, in a study by Danieli, people played this game repeatedly for 300 trials. The cooperation rates in the last 50 rounds were around 80%, which could suggest that it is potentially important to integrate a tendency to cooperate and other regarding preferences to behavioral epidemiological models. Yet, there are two reasons why I think this phenomenon is not as important as it may seem at first. First, results were obtained here when the pairs of participants playing the game remained fixed for all 300 rounds. This is called fixed matching. The same two people play with each other in all rounds. In epidemics, however, we interact with many different people all the time. That is, we do not have a fixed partner. Danieli also ran another condition, probably more relevant for epidemics, that is called random matching. Here, 4 people played this game, still in pairs and still for 300 rounds, but now the pairs were randomly matched among these 4 people in every round anew. The results of this random matching show that cooperation does not increase with experience. Actually, it tends to decline. A second reason why a tendency to cooperate may be less relevant in epidemics is the experimental finding that cooperation rates are usually smaller when the outcomes of the player depend not only on the decisions of the other player, but also on some probabilistic function, just as before in decisions under risk and uncertainty. That is, in this original game, provided we know the action of each player, the outcomes of each player are certain and determined. Yet, in an epidemic, there is no such certainty. Outcomes are probably probabilistic even after holding the actions of all players fixed. Now, if we then turn these numbers to probabilistic, then we see often that cooperation rates decline even under fixed matching. This phenomenon that cooperation rates decline when outcomes are probabilistic was found in many other types of games as well, not only Prisoner's Dilemma, suggesting that other regarding preferences are not very robust when outcomes are noisy, as in epidemics. Yet the fact that we make decisions in social contexts can have other effects on our behavior, even over time, and these can be important for modeling behavior in epidemics. Here I listed several possible effects of learning from others. First, there is a phenomenon of imitation of others that can make us simply copy the behavior of another person. Second, we may learn from another person's outcomes. Specifically, we can see if what that person does turns out to be successful or a mistake. When we learn from the outcomes of others, the chances of us doing what works most of the time increase because we normally see what happens most of the time and not the rare event. Third, we sometimes learn from another person's actions or strategies rather than the outcomes of these actions or strategies. Here, the idea is that we may observe another person doing something we had not even considered before. Now, this new strategy may enter into our consideration set of alternatives, which naturally increases the chances that we will act on these strategies, even if they turn out to be poor strategies. Finally, the most natural impact of others on our choices is that their decision may change the incentive structure for us, thus changing our behavior as well. To demonstrate the point that other people's behavior can change the incentive structure, consider the adaptation of the panic and responsible task from before. Here, irresponsible behavior, here it's panic, is contagious. The idea here is that if other people panic and empty the shelves from toilet paper in the supermarket, it becomes less and less rewarding to be responsible by not buying toilet paper. That is, the existence of some irresponsible agents may reduce the incentives for others to behave responsibly. The irresponsible behavior is then contagious. Again, we simulated artificial agents in this game and see that both agents who rely on small samples and rational agents quickly learn to panic due to this behavioral contagion. Just as a complement, here is a contagious, reckless, or responsible game, where the irresponsible behavior here is reckless and it reduces the incentives of others around to behave responsibly as well. And you can see here also that agents again become more reckless more quickly, both rational and agents who rely on small samples. I want to finish with a few words on applications. Because in epidemics, people's decisions are probably based on experience and feedback from previous similar decisions, it is probably going to be very hard to get people to behave responsibly. For two main reasons here. First, reliance on small samples, which implies recklessness. Second, the fact that irresponsible behavior can be contagious. But we can also use our understanding of the way people behave when they can rely on feedback to design environments in which people will naturally behave more responsibly. Recall, reliance on small sample implies underweighting of rare events. But the other side of this coin is that reliance on small samples implies high sensitivity to the frequent outcomes, the non-rare events. Therefore, if we could design environments in which the frequent outcomes from responsible behavior is better than the frequent outcome from reckless behavior, then we may expect people to behave more responsibly. We recently demonstrated this idea in a field study among nursing home employees. The management wanted them to use a contact tracing application when inside a facility so that they can have quick epidemiological investigation in case of infections. But most employees did not use the app. We therefore designed an environment in which doing the responsible thing, here using the application, was frequently rewarding. We simply asked the management to allow employees 2 ways to enter into the facility at the beginning of their shift. Those who have the app and use it could enter using a QR code embedded in the app. Those who do not use the app continued entering just as they did before. This implied that they had to wait in queue to be checked by the security guard for their temperature and be asked a few questions on their whereabouts since they were last here. In practice, this meant that using the app saved the employees just a couple of minutes every day when entering the facility. These are the results for the number of users of the app over a 9-week period. We first measured behavior at baseline over 5 weeks. And then the red vertical line here is the day that our intervention started. As you can see, the intervention more than tripled the number of users of the app. And this behavior change sustained over at least a 4-week period. To summarize, to model behavior in epidemics, it is important to consider that the classical decision research like prospect theory and other regarding preferences may be less relevant for epidemics because it focuses on decisions that are not made repeatedly and that cannot rely on previous feedback. However, in epidemics, many of our ongoing and relevant decisions can rely on feedback from previous experiences. The decision from experience literature studies the effects of feedback, and it finds that reliance on small samples is a very useful assumption to make in models that try to capture behavior in such settings. In addition, it is important to consider the role of social learning and how that impacts behavior. From a practical point of view, the message is simpler. It is important to consider the possibility that to get people to behave more responsibly, we should just make the responsible choices rewarding most of the time. Thanks for listening.